Bismillahirrahmanirrahim. And dear students, we'll start lecture number 1 of week number 15 on stochastic processes. This is a higher concept on the course in the course of probability and random variables. What do we mean by stochastic processes, and what are the basic concepts of stochastic processes we'll handle in this particular lecture and in the next lecture. So first, the definition of a stochastic process. A stochastic process basically is the association of time functions to outcomes of a sample space. So I'll write that a stochastic process x of t. Remember, time is a basic entity in a stochastic process. So a stochastic process x of t consists of an experiment with probability measure say p dot defined on a sample space S and a function that assigns a time function x of t comma s to each outcome S in the sample space. Of the experiment. Please understand this carefully. A stochastic process, the notation is x of t, and it consists of an experiment with some probability measure defined on a sample space S. So the sample space of the experiment is capital S, and then we have a function or a relationing which relates time functions, call them small x of t comma s to each outcome s. This is one of the outcomes in this particular sample space of the experiment. So small x of t comma s means a time function, which is one function out of the many possible functions in the process x of t. So this capital X indicates now the stochastic process. If you recall, we had random variables like capital X, capital Y, and then we had small x and small y. So small x and small y were the values of those random variables, capital X and capital Y. Similarly, capital X of t is the process, stochastic process, and this small x of t is one of the time functions associated with this sample value of the experiment with sample space S. So this is one time function of this process, time function. So that's why we have this t, and this small s indicates a particular value from this sample space. So we call this x of t, small x of t comma s, as a sample function, because this is one of the many functions possible in the process x of t. So we have now another definition which is about sample function. So a sample function x of t comma s is the time function or call it time waveform associated with outcome S, with outcome small s of an experiment. If you can understand this, the remaining part of the lecture should become a bit easier. Uh, this is your capital S, which is the sample space of certain experiment. This is small s, which is one of the possibilities in this sample space. This is the time t. This x, small x, is one of the sample functions from this process, capital X of t. As you have random variable capital X and then you have small x, which are the samples from that random variable x. Similar is the case with the process. Capital X of t is the process and small x of t is the sample function, one of the sample functions in this process x. And S basically indicates to which sample from the sample space this x of t is associated. So this x of t is now a sample function, t is the time and s is an outcome of the process. So how we can visualize a stochastic process? Let me give you a little more on this. Suppose you have some sample space S where you have S1, S2 and S3 as the samples. What we mean by associating a time function with the outcome S1 of the sample space is basically this. Say you have some function of time which is associated with this outcome of this sample space. So you call it x of t comma s1. The sample function x from the process x of t, but associated with a sample function, sample value s1. You can have another function of time, call it x of t, so t comma s2, which is now a sample function associated with the sample s2 of the process, something like this. And similarly, you can have another function of time and sample function x of t comma s3. So this is the sample function associated with this sample from the sample space. Suppose something like this. So now you see, this is a figure that relates time functions x of t comma s1, x of t comma s2, x of t comma s3 with the sample values from the sample space of an experiment. Remember, experiment is the basic entity in any stochastic application, in any probability related consideration. So now you see the sample space of the experiment are these three outcomes, and the ensemble of the sample functions. Ensemble means all the sample functions considered together. All parts of a thing taken as a whole. This is what we mean by an ensemble. So here the ensemble means all the sample functions considered together. Now let's have a little more understanding about the time and the process X. So suppose we choose this particular time instant, which means we pick this value of the process from this sample function when we fix time at say t1 on this time axis. So now this is basically t1 comma s1, sample function 1, sorry, yes, sample value 1, time fixed at t1. The same time fixed here, from this sample function you get t1 comma s2, and similarly here you get another point t1 comma s3. So all this is obtained by fixing or considering the time t1. So now what we see here is that we have a sample function, we have a sample space, we have three sample functions associated in the process with these sample values. When we fix time, we pick one value from each of the sample functions. So you get some s from here, another s from here, another small s from here. So you get three values, and the sample space also has three values. So this is now one random variable that is extracted from this stochastic process. You see, these are these may be three different values. Suppose you fix time at another time instant, just assume, and now we have, say, this, call it t naught for a while. So we have one sample value here, we have another sample value here, and we have another sample value here. So you see, this is another random variable. So here we have obtained a random variable by fixing time at t1. So the random variable is x obtained at t1, and the random variable here is basically x obtained, say, at t naught. So you can have many possibilities of such random variables. So now the conclusion, one of the conclusions, when you fix time or when you freeze time at an instant, you obtain a random variable from a stochastic process. This is important to understand. When you fix time, when you freeze time at a particular instant, you obtain a random variable out of the process. So you see there, you can see there can be many possibilities of random variables. So many random variables possible from this particular stochastic process. So this is one of the understandings of the concepts. I'll move on to the concept of averages in a stochastic process. So now you hopefully understand what we mean by an ensemble, what we mean by a sample function, and what we mean by a random variable obtained from the process x of t. The process is x of t. So you see, this is a process x of t. This is a random variable capital X of t naught. Please note the conceptual difference and the notational difference. A process will always contain a generic time t, and a random variable will be indicated by fixing the time at certain instant, say t naught, t1. So these are the two random variables. There can be many more random variables possible from this process x of t. You just need to fix the time t at an instant. So this was the basic concept. Now we move on to have two more concepts. First is the ensemble average, and the other is the time average, and then I'll give you some interesting comments on these. Ensemble average would mean the average uh, of, say, this random variable, because the average is taken using this value of the random variable and this value of the random variable and this value of the random variable. So you have utilized the total ensemble to find the average of this random variable. So you call it the ensemble average. So when you fix time t at, say, t1, x of t1 is a random variable and its average will be called ensemble average. Is ensemble average a constant or a random variable for a particular process? This is another important question. So I'll repeat the question. Is ensemble average a constant or a random variable? What do you feel? I believe this is a random variable. The answer or the argument is as follows. You fix time at t1, you get some ensemble average. You fix time at t0, you get another ensemble average. You fix time at, say, any other instant of time t, you may get a different average. And so you are not sure what average you will obtain, and hence we call ensemble average as a random phenomena. Ensemble average is a random variable. So now please note this, that ensemble average is random. Always remember this, because you have obtained the average by utilizing this. When you fix time at t1, but you obtain a different average from these three sample values by fixing time at t0. So at each different time instant, you may obtain a different average, different ensemble average, and hence ensemble average is a random variable. The other concept is the time average. Time average would mean that you take a particular sample function and then you take some time interval on on the axis t, and then you take the average. So say from ta to tb, you take the average of this function and you'll have some average value. Now my second question, what do you feel? Is this time average a random variable or a constant? I'll repeat. When you take average like this is called ensemble average, and this is a random variable as per my arguments and discussion. The other type of averages in stochastic process is a time average. Time average would mean average on time. So you take certain time instants and you take the average of the function within this time interval, and so you get a time average. Now the second question is this time average a constant or a random variable? You see, if you take the time from ta to tb, you will have some average value, but this value may be different from the average between, say, ta1 to tb1. So you have a different average here. You have a different average in this interval. You have a different average in this interval. You may have a different average in this interval, and so on. So it depends on the time interval, and hence we can claim that time average is also a random variable. So my next important point is time average is a random variable. So the ensemble average is a random variable. Time average is also a random variable. I'll go back to my first slide and give you a quick revision of this, because this is important to understand. A stochastic process basically associates time waveforms or time functions with the outcomes of a random experiment. So the outcomes are all listed in the sample space of the experiment. The process is given capital notation. T is always there because it's a stochastic process. A time function is associated with each outcome of the process, and that time function is denoted by the small letter of the name that is given to the process. So capital X of t is the process, and small x of t is one of the time functions or one of the sample functions from this process, and this s, small s, indicates one of the sample values from this sample space. So this is now a sample function. We can plot this example. For this experiment, we have a sample space with, say, 3 sample values. Each sample value has some associated waveforms associated with it. Call it x of t comma s1. Similarly, s2 has an associated waveform x of t comma s2, and similarly x of t comma s3. So these are the 3 different waveforms. This is one sample function, this is another sample function, this is another sample function. So all these waveforms considered together is called ensemble of the process. So now we see that if we fix time at, say, t naught, if we fix time at t naught, we obtain 3 values of the random variable x of t naught. So capital X of t naught is a random variable obtained from the process x of t. Similarly, x of t1 is another random variable obtained from the process x of t. So you see now t naught is one fixed instant, t1 is another fixed instant, but t is the general time. So you have this random variable, you have this random variable, you may have many other random variables possible from this process. So all these random variables can have averages as well. So now we see 2 more concepts, the ensemble average and the time average. The average of this random variable taken on all the ensemble, and which means this value, and this value of the random variable. So this is called ensemble average. An ensemble average is a random variable. Why it is a random variable? Because when you change the time instant, say from t1 to t0, you may have a different random variable and hence a different average, a different ensemble average. So my conclusion is that the ensemble average is a random variable. The other kind of averages in a stochastic process is the time average. Time average is simply average taken over a time. And my second important question was, is time average a constant or a random variable? So we see that if we fix the time interval, we get some average value. We take another time interval, we get another time average value. We take another time interval, we may get another time average value, and so on. So it means that the time average is also not fixed, and hence we also claim that time average is also a random variable. So this was a quick basics of the only the initial basics of the concept of stochastic processes. I'll give you uh, some hint on the types of stochastic processes. So my next small brief topic is types of stochastic processes. There can be, in general, four types of stochastic processes. If you see, there is the concept of time and the concept of value of the function, the height of the function. So we basically divide the types of the processes with respect to time and with respect to the value of the sample function. So the types can be divided into four categories. The types of the stochastic process can be divided into these four categories. So the state of the process, which means the height of the function, and the time variable in the process. So now I have just two axes, the time axis and the state axis, or the value of the process. First type is continuous time, continuous state process. So here you see the process can have any possible state on all the continuous time. Here this is a continuous time but discrete state process. Why? Because the state of the process can be any of the two values, either say this higher value, this or this, but there is no other possibility. So if you call this as +1 and this as -1, so this process can have either a +1 or a -1 at any instant of times, and hence the time is continuous in this type and the state is discrete. So this is a continuous time discrete state process. This is a discrete time continuous state process, which means the time is discrete in nature. So you pick the value of the process at a fixed interval of time, but the value of the process or the state of the process can be any possibility within a continuum, and hence this is a discrete time continuous state process. And the last one is discrete time discrete state process, which means the time interval on which the process state is picked is discrete in nature, and the possibilities of the states are also discrete in nature. Here we see that it is either +1 or a -1. So these are the four examples of the stochastic types of stochastic processes. But can we think of the of some of the examples of these processes? For example, I pick this one, where the time is continuous and the state of the process is continuous. Can you think of an example of such process? Let me give you an example. maximum temperature at a place in the interval say 0 to t. The maximum temperature at a place in the interval 0 to t. So you see 0 to t in this interval, uh, the maximum temperature can exist at any instant of time, and the value of this maximum temperature can be any temperature value. So that is why this is an example of a continuous time, continuous state process. What about the example for this type, where the time is continuous but the state is discrete? Can you think of an example for such type of processes? I give you one. The number of phone calls received in a time interval say 0 to t. So the number of phone calls can be a discrete value, either no call, one call, two calls, three calls, whatever, but discrete in nature. And so this is a continuous time. You can receive call at any instant of time within that interval 0 to t. So your time is continuous in nature, but the number of calls will be discrete. There is no such thing as 1.5 calls, 1.51 calls, and so on. The calls will always be discrete in nature, either no call, one call, two call, three calls, four calls, whatever, but the discrete number. So the example for this type is the number of phone calls received in some interval of time. What about example for this type, discrete time continuous state process? Here the example is temperature at the end of nth hour of a day. So you see, you are taking the temperature or measuring the temperature at say at the end of every hour in a day. So your time is fixed, say 12 o'clock, 1 o'clock, 2, 3, 4 o'clock, 5 o'clock, and so on. So say 12 o'clock, 1 o'clock, 2, 3, 4, 5 o'clock, and so on. So your time is discrete, but the temperature that you measure at that time instant may be different at any observation. And hence, this is an example of a discrete time but continuous state process. What about this one? This should be easy for you because the time is discrete and the state is discrete. Can you think of an example of such type of processes? We have done it many times. We have done such examples, related examples, many times in the course. I'll give you one example. For this discrete time, discrete state process, an example is the outcome of the nth toss of a six-sided fair die. So you see, the state of the process is the values on the dice 1, 2, 3, 4, 5, 6. There are just 6 possible values, and this is the outcome of nth toss. So on the first toss you will have some value from 1 to 6. On the second toss you will have some value from 1 to 6. On the third toss you will have some value from 1 to 6, and so on. So you can have 6 possibilities, 6 states of the process, and you are counting it with respect to time, discrete time. First toss, second toss, third toss, fourth toss, and so on. And on each toss, the range of values can be from 1 to 6. So it is a discrete range. And so this is an example of a discrete time, discrete state process. So dear students, now we have been able to discuss the types of 4 types of processes, stochastic processes with respect to the state and time. We have given a few examples of about that as well. But I told you we can obtain random variables from a random process or a stochastic process. Remember, stochastic process and random process are the two names of the same concept. So whenever I say a stochastic process, it also means a random process. And whenever I say a random process, it automatically means a stochastic process. This is just two different names of the same phenomena. Now, I'll do one example to also give you the concept on how to obtain or discuss random variables from a process. So the statement of the example, we say let x of t is a process defined as r times absolute of cos 2 pi ft. Let x of t be a rectified cosine signal with random amplitude r with the exponential PDF f sub r of r, and that is equal to 1 over 10 e raised to power minus r by 10 for r greater than or equal to 0 and it is equal to 0 otherwise. What is the PDF of the process, which means PDF p sub x of t of x? So it is important to understand the notations here. This is the PDF of this random variable r. It is already given that this r, which is now the amplitude of a rectified cosinusoidal signal, and the amplitude is random in nature, and the randomness is determined through this PDF of this random variable r. So you see we have associated a cosinusoidal time function with the random variable r, and hence this all is nothing but a process x of t. The PDF of this random variable is already given. We are required to find the PDF of the process. The notation for the PDF of the process is simply f sub x of t. For the random variables, the PDF of the random variables, you wrote f sub x of x, but for the PDF of a process, you will write f sub x of t of x. So this is the notational difference here. How to find the PDF of the process when you are given the PDF of the inherent random variable in the process? So let me approach this and solve this. You know that the probability that the process is less than or equal to this value is nothing but the probability that or absolute cos 2 pi ft is less than or equal to x. The process, this is the CDF. So the probability that the process is less than or equal to this value is basically this. I have simply substituted x of t with this, nothing big. So I can write it as the probability that r is less than or equal to x over absolute cos 2 pi ft. And so now you can find this probability, since you know the distribution of r here. This is the PDF of r here. So the CDF is simply integral from 0. Why? Because r is going from 0 onwards, 0 to this particular value. You see, this is the expression of a CDF. Probability that r is no greater than this value by definition of CDF. So the integral is from 0 to this highest value, x over absolute cos 2 pi ft f sub r of r dr. So when you integrate a PDF, you obtain a CDF. You know this. So when we integrate this, we will obtain, and you know, f sub r of r is nothing but 1 over 10 e raised to power minus r over 10. So when you integrate this, you will get 1 minus e raised to power minus x over 10 times absolute cos 2 pi ft. You have to solve this integration. So you see, this is now effectively the CDF of the process. So if you have the CDF of the process, you simply differentiate it and can find the PDF of the process. So the CDF is meaningful in this range where x is greater than or equal to 0, and otherwise it is simply 0. So you don't even need to consider this. So now that the CDF of the process is understood, we can always differentiate it and find the PDF. And therefore, the PDF of the process x of t is nothing but d f sub x of t of x over dx. You obtained, through this mechanism, you obtained the CDF of the process. CDF of the process was obtained by utilizing the distribution of the random variable in the process, which is r, and this is exponentially distributed. So we simply used the concept and the definition of the CDF and ultimately obtained this expression, which is the CDF of the process x of t, the total process. And from there you can differentiate the CDF of the process with respect to x, and you can obtain the PDF. And when you do this, I think you can do this easily. You will see that your PDF becomes 1 over 10 times absolute cos 2 pi ft e raised to power minus x over 10 times cos 2 pi ft. So you see, this PDF of the process is also an exponential PDF, because if you remember, in the PDF of an exponential continuous distribution, it was a e raised to power minus ax. So a here is 1 over 10 absolute cos 2 pi ft. So hence we see that the process x of t is an exponentially distributed process where these are the parameters of the distribution. So, dear students, we have been able to do a nice quick example on how to find the PDF of a process. This is simple. You always have some random variable associated with some time function in a stochastic process. The random variable distribution is already given. We are asked to find the PDF of the process. The notation for the PDF of the process is now f sub x of t. There is a little difference between the PDF of a random variable, which is denoted as f sub x of x. The PDF of the process is f sub x of t of x. So, as you know, in continuous nature problems, we start with CDF and then differentiate the CDF to obtain the PDF. So we started off with the CDF like this. This is by definition the CDF, and then we placed R here in the form of a CDF, and then we integrated because this probability is from 0 till this value of R. So we integrated from 0 till this value of R, the PDF of the random variable. And this is already given. So when you integrate this, so you simply place 1 over 10 e raised to power minus R by 10 here. And then you integrate on this limit, you will obtain this. So this is your CDF of the process, stochastic process x of t. Now the rest is easy. You simply differentiate the CDF with respect to x and you will obtain the PDF of the process. We notice that the random variable R is an exponential random variable and that is associated with the stochastic process with by using this particular time functions. The PDF of the process is also an exponential PDF. I'll stop here and in the next lecture we'll inshallah discuss the concepts of stationarity and then we'll end the course. Thank you very much for your time today.